Hello! In this video, we are going to prove the following theorem. E to the x is greater than or equal to 1 plus x for all real numbers x. Now, let's first remind ourselves what e to the x is. The limit of 1 plus x over n to the power of n is equal to e to the x for all real numbers x. Now, in proving this theorem, we are going to use Bernoulli's inequality, which says the following. Suppose a is a real number greater than or equal to -1, and n is a positive integer. Then 1 plus a to the power of n is greater than or equal to 1 plus na. And we are also going to use the following preliminary result involving convergent sequences of real numbers. Suppose xn is a convergent sequence of real numbers, and a is a real number. If xn is greater than or equal to a for sufficiently large n, then the limit of xn is also greater than or equal to a. So what this result is essentially saying is, if we can find a point such that every term of the sequence beyond that point is greater than or equal to a, then the value the sequence converges to must also be greater than or equal to a. Okay, so now let's get into proving this theorem. To start out the proof, let's give ourselves an arbitrary real number x. And from here, we want to show e to the x is greater than or equal to 1 plus x. And to show that, the thing to observe here is, in our final preliminary result, if we take xn to be the sequence 1 plus x over n to the power of n, and we take a to be 1 plus x, well, if we can show that 1 plus x over n to the power of n is greater than or equal to 1 plus x for sufficiently large n, then it will follow that the limit of 1 plus x over n to the power of n is greater than or equal to 1 plus x. But the limit of this sequence is precisely e to the x, so we will have shown that e to the x is greater than or equal to 1 plus x, which is exactly what we want. So we want to show that 1 plus x over n to the power of n is greater than or equal to 1 plus x for sufficiently large n. So how do we show that? Well, let's first choose a positive integer capital N greater than negative x. And the claim is, for all integers n greater than or equal to capital N, 1 plus x over n to the power of n is greater than or equal to 1 plus x. So how do we show that? Let's first give ourselves an arbitrary integer n greater than or equal to capital N. Now, since n is greater than or equal to capital N, and capital N is greater than negative x, we have that n is greater than negative x. So if we take this inequality and divide negative n on both sides, we're going to get x over n is greater than negative 1. So now we apply Bernoulli's inequality. Applying Bernoulli's inequality, we'll take a to be x over n, and we'll take n to be n, and with these choices of a and n, we have that 1 plus x over n to the power of n is greater than or equal to 1 plus n times x over n. But this is precisely equal to 1 plus x. So what this tells us is that 1 plus x over n to the power of n is greater than or equal to 1 plus x for any integer n greater than or equal to capital N. In other words, we've shown for sufficiently large n, 1 plus x over n to the power of n is greater than or equal to 1 plus x. And so by our final preliminary result, it follows that the limit of 1 plus x over n to the power of n is also greater than or equal to 1 plus x. But the limit of the sequence is precisely e to the x. So we have that e to the x is greater than or equal to 1 plus x. And we have shown that e to the x is greater than or equal to 1 plus x for some arbitrary real number x. Well, since x is arbitrary, this means we have shown e to the x is greater than or equal to 1 plus x for all real numbers x. And so this completes the proof. And so yeah, that's pretty much it for this video.